binomial variables or dichotomous variables are categorical variables that contain only two values. Male, female, have diabetes, don't have diabetes, high blood pressure, normal blood pressure, male or female, right-handed, left-handed, and so on and so forth. Okay, a lot of times we'll express them as proportions, like the percentage of people in a population that are male. The prevalence of diabetes in a population is 10%. 10% means that out of every 100 people in that population, 10 of them have diabetes, right? So you have, if I said a D plus for diabetes and D minus for doesn't have diabetes, we would have 10 D pluses and 90 D minuses for a 10% prevalence. Okay, that's the way we might put, or yes and no, and so on and so forth. That's the way we might enter that into SPSS, for instance. SPSS, we might code it so that a 1 represents you have diabetes and a 2 represents you don't have diabetes. And we'd have 10 ones and 90 twos and so on. So very frequently we'll describe that as a proportion. Okay, so one of the things that's of interest to us, and we were working on this when we were talking about probabilities, is what's the probability? Let's say I went out into a population where I know the prevalence of diabetes is 10%. What's the probability that I would pick one individual from that population that has diabetes? Well, since prevalence is 10%, we would expect if we take 10 people, one of them will have diabetes. Is that going to happen every time? No. Every once in a while, I'm gonna take 10 people. Maybe I'll have nobody that has diabetes. Very frequently, I have nobody that has diabetes because the prevalence is so low. The most common outcome that I would expect is 10%, is 1 out of 10 if I take 10 people. If I did it again, it might be 2. Very rarely, it might be 3 or 4 out of 10, right? If I just happen to, sample the people and they come up that way. So that's sampling. That kind of distribution, if you can imagine it, kind of makes a kind of histogram where the top of the histogram is 1 out of 10 and 2 out of 10 is less frequent, as is 0 out of 10, and 3 out of 10 is even less and even less. So we get kind of a histogram. In fact, if I were to do that with coin flips are a little bit more friendly to this idea. If I would do this with coin flips, you would say that if I took 100 coins and flipped them, that the most likely outcome, most common outcome, would be 50 out of 100 heads, right? But how often would that really occur? If you really think about it, if you flip 100 coins, you wouldn't expect to get 50 out of 100 heads very frequently, right? I mean, you'd have to be pretty lucky to get exactly 50 heads and exactly 50 tails, even though that's the most likely outcome. 49 and 51 heads are probably the next most likely. So if we make a histogram, they're going to be a little bit lower than 50%, 48 and 52 and 47. So our histogram is going to look something like this. Forgive me, I'm using my finger because I can't get my trackpad to work with this new computer I have. I'll have to work on that. So this is kind of what it would look like, right? And if I repeatedly took 100 coins and flipped them, the most frequent outcome that I would expect to get is 50 heads, right? 50 heads. Okay, and then a little less frequently. And so half of the time I would get 50 or less, and half of the time I'd get 50 or more. Because, if I look at this as kind of a normal distribution, it isn't really a normal distribution because it's not a numerical variable. It's a categorical variable, and we're just dealing with proportions. If this were, I can kind of look at this, it's kind of like a normal distribution, symmetrical, about the mean, and so on and so forth. But the numbers, the height represents the number of heads that I would get for a sample size each time I tried it of 100. Now, I wouldn't expect to get very many times when I get 30 heads out of 50. That's actually probably a pretty rare event. But, how do we know how rare an event that is? Well, we learned that that there's a formula that represents this kind of probability, that binomial formula. Use some exponents and so on and so forth. When we were doing it with only a sample size of 3 or 4, it wasn't a big deal to do this. But when we were doing it with a sample size of 100, right? That's going to get, we're going to get exponents to the 99th power, and it's going to get pretty nasty, right? So fortunately in Excel, which I have here somewhere, so if I can't find it, I'm going to have to search for it here. Excel. In Microsoft Excel, we have a function which will do that calculation for us, that rather involved calculation. Look, it's transparent. Okay, let's try and close that. Whoops. Oh, excuse me. I have to go over here and tell it I want to use the pointer instead of the pen. So to close that, and I can open it this. Okay, and I'll change my view so we can actually see this. Okay, so what's the probability in this case, for instance, with coin flips? What's the probability that we get 48 heads out of 100 flips? Well, I can use the binomial distribution, equal binom dist, as we did in class, binom dist. When I hit the parentheses, it prompts me for the parameters that it needs to complete this, right? So what's it asking for? The number of successes, the number of trials, the probability of success on any individual coin flip, and cumulative or not cumulative. So if my question is, what's the probability of getting exactly 48 out of 100 coins being heads, right? I'm going to put in 48, comma, 50 for the number of trials, comma, the probability is 0.5, half for each coin flip, and cumulative, if I ask that question exactly 48 out of 100, I'm going to put false here because I only want that specific probability, not that. We'll talk about cumulative in a second. What's the probability of happening? Probability of that happening is really tiny, right? But that doesn't seem right, does it? Because 48 is not that distance. Well, that's the probability of exactly 48, not. Oh, excuse me. I made a mistake. It's 48. It's 100 trials, right? We're flipping 100 coins, right? It's about 7% likelihood I would get that exact outcome. But I could use the same function another way. Binom dist parentheses. I could say, okay, number of successes is 48, comma, number of trials is 100 coin flips, 48 coin flips out of 100, and the probability for each one is half, 50% that I would get ahead. Now, if I put in true there, what that will give me instead, what that will give me instead, the probability of 48 or less. In other words, probably a 48, we're getting exactly 48, probably going to get exactly 47, probably 46, all added together. Hence, true for cumulative, everything to the left of that. Okay, and that, whoops, I made a mistake there. Let's see. Yeah, I kind of wiped that out. Let's see, 48, 100, 0.05. I think we're set. That's 38%, right? That sounds realistic, right? Probability of getting 52 or more. Okay, what's the probability of getting 52 or more? What's the probability of getting 52 or less? Equals binom dist, parentheses, 52 heads, comma, whoops. Get used to this new keyboard. Binom dist, 52 heads, comma, 100 trials, 100 coin flips. 0.5 is the probability any individual coin, and cumulative is going to be true. And this is going to give me the probability of 52 or less. I'm interested in 52 or more, but I need to do this way because the function will only give me the probability from that point down. And that comes out to be 69.13. So now I want to know what's the probability of 50 or more. Well, if that's 69.13, if that's 69%, the probability of being above 50, having more than 52 out of 100 is going to be what's left, or 1 minus 69%. So that's going to be equal to 1 minus the result that we just got for 52 or more. And look at this, it's 52 or more. Did I get that right? 52, 48. Okay, it's going to be the difference between those two. Not exactly symmetrical, but at any rate, this is what we're describing here is the binomial distribution. Notice how it looks very much like a normal distribution. It's not behaving exactly like a normal distribution, but it looks like a lot like it. So what we can do is we can say to ourselves, can I describe this in the same way I would describe a normal distribution? The answer to that is yes. You can look at this as an approximation of a normal distribution. Well, what's the average? If I took 100 coins and flipped them, what would I expect the average number of heads to be? Well, in this case, the average number of heads is going to be 50. How can we get that from what we know now? Well, we can get that by saying, and the mean, mu, let me get the pen on. Mu is equal to n, the sample size, times the probability, n times p. So that's equal to 100 times 0.5, or 50, equals 50. Right? So the mean can be described as n times p. What about the variability here? The variability uses another formula. Standard deviation, which indicates the variability, is equal to the square root of the sample size n, the number of coin flips, times the probability of heads, times the probability of 1 minus heads, which we're going to call Q. You could call it 1 minus P, or you could call it Q. N times P times Q, and the square root of that. So in our case, what is that? It's the square root of 100 times 0.5 times 0.5, 1 minus the probability. So 0.5 times 0.5 is 0.25. Times 100 is 25, so it's the square root of 25, which is equal to 5. So how does this help us? Well, this helps us because then now we can say that if I look at this as a normal distribution, I can use this as an estimate and say, well, 95% of the results are going to be between 40 and 60. 2 standard deviations below the mean and 2 standard, just like I would have with a normal distribution. That's called a normal approximation to the binomial distribution. Do I think you're going to use this very much? I doubt it, right? Is it on the exam? I honestly don't remember. I think I usually avoid putting on this exam because I don't think it comes up that much in real life. So, but keep that in mind. Now, what if we were talking about our example with diabetes, where the probability is 0.1? So if we took a sample, so if our sample size is going to be, let's say 20, right? What would be the mean of repeated samples of size 20? It would be n times p, which would be 2, right? So the mean number of people with diabetes out of a sample of 20 that I would expect to get is 2. What's the variability? Well, the variability, sigma, is equal to our standard deviation. The square root of n, which is 20, times 0.1 times 0.9. 0.1 times 0.9 is 0.09. And 0.09. Whoops. I got to turn that off again. Let me put it down here. It's 0.09 times our sample size, which is 20, is equal to 1.8. And the square root of that is 1.34. Our standard deviation would be 1.34. Now, that's certainly not going to be as interesting or as good an approximation as our example where we had a probability of 0.5, we had the nice normal distribution. Instead, we're probably going to wind up getting something that looks more like this. Keep in mind that you can't go below 0 out of 20, right? So 0 out of 20 is going to be here somewhere. So our distribution is going to look something like this, kind of truncated, right? Where the mean or the mode is going to be 2, right? So it's got to look a little bit, it's not going to be as nice a normal distribution, but at least you have a way to approximate what this distribution is going to look like without calculating every individual probability. Okay, so that's what question, let me just go to that homework and that question and see what it actually says. Let me clear this off so we don't have to look at it. Erase all drawings. Good, that went away. I've got the hang of this. Let's go back here to assignments. Up. I think I must have something else open here that's getting in my way. Oh, I still got the pen on. Oops. Didn't mean to do that. Get that out of the way. Actually, I think it should let me log back on without logging on. Yeah, there we go. So homework 3B. Question number 5. Here we go. 40% of Hells Angels have a mom tattoo. What would be the mean number of Hells Angels and mom tattoos for repeated samples of size 50? So the sample size is 50. The probability is 0.4. So n times p give you your mean. 40% of what would be the standard deviation for the number of Hells Angels with mom tattoos for repeated samples of size 50? That's going to be the square root of n, 50 times 0.4 times 0.6. Okay, so when you guys, go back and redo your homework and stuff like that, that should help out on that. Using normal approximation binomial distribution z-table, what is the probability a random sample of 50 Hells Angels will produce more than 25 bikers with mom tattoos? Okay, so now there's 2 ways we could do this. The more precise way is to use binomial dist because it comes up with the exact probabilities, right? Binomial dist, comma, 25 successes, comma, 50, comma, 0.4, comma, true for cumulative will give you less than that, right? So to get more than 20, the probability to have more than 25 bikers out of 50 would have a mom tattoo is 1 minus the result of that, right? Because it's going to give you to the left of 25, not to the right of 25. Okay, if you do this, what's described here, and apply the normal distribution to this, the normal approximation to this, you're going to get a slightly different answer. And chances are, depending on how, usually I put down a number, which is the right answer, but then I give you a range. If I were careful, I would have tried to make the range such that I knew you used the normal approximation like they're asking instead of the other way, the binomial dist. I don't know. Probably it could be I made the range wide enough that it would work with either, but I couldn't tell you that without giving it a try. So at any rate, so in this case, if we use this that distribution, using normal approximation, what is the probability a random sample of 50 Hells Angels would produce more than 25 bikers with mom tattoos? Okay, 25. The mean. The mean is 50, 40% is 20, right? So the difference between 20 and 25, x minus mu is 5, right? 5 is 25 is what we're interested in, minus the mean, which is 20, would be 5 over the standard deviation, whatever that, let's see what the standard deviation comes out to. Whoops, that's my contacts. I want my calculator. Okay, so 5 over the standard deviation. Standard deviation is going to be sample size is 50 times 0.4. Oops, I messed that up. Clear it out again. Is 50 times 0.4p times 0.5, 0.6. Unfortunately, this doesn't let you just erase the last one. 50. I'm gonna have to click it in, so I know I got it. 50 times 0.4 times 0.6 equals 12, and we take the square root of that. It's going to be 3.46. Now, if we want the z-score for this, the z-score is going to be 25 minus 20 is 5 divided by the standard deviation, 3.46. I'm going to put this into memory. I'm going to clear it. I'm going to say 5 divided by 3. Whoops. Okay, I'm going to do it from scratch. 5 divided by 3.46. I'll do it the hard way. Comes out to a z-score of 1.45. Now, if I go to the Agresti z table, right? Let's see if I have it on this computer. I hope I put it on here. Yeah, let's see, is it here? Let's see. I think that's it. Go to the Agresti z table. I'm going to look up the z-score for 1.45. 1.401234. So it comes out to be about 92.7%. 92.7% is less than that, but we asked what's the probability of more than that, so we would subtract that from 1. So 90, what was it? What did I say? Was 1.45? 1.4. 0, 1, 2, 3, 4, 5. I'm sorry, 92.8, I guess. Nope, this is it. No, I've got it wrong. 92.65. So I'm going to call 92.7. So that would be 6.3% would be, okay. And you can, and I think it asks for you as a probability. So it's if it asks as a percentage, it's going to be a percentage. If it asks for it as a proportion or a probability, put in 0.6, whatever it came out to be. Okay, makes sense? Right, 1 minus, because this table always gives you, remember it's a positive z-score, because 20, the mean is 20 for this distribution, and the number we're interested in 25, so we know it's to the right of the mean. And we use a table, or if we use Excel, it's always going to give you the area to the left. So it's going to be 50% plus what's on the other side of the mean, so always going to be more than 50%. Unless it's a negative z-score. If it's a negative z-score, like if I ask 15 instead of 25, that'd be 15 minus 20 minus 5. So that'd be on the other side of the distribution. It'd be negative 1.45. Right? And that would be, we know, less than 50%. So it's you can kind of check, just the man I need. Could you turn that on for me? Okay, good. I tried to get you on the phone, but.
No, nobody answered?
No, that's okay. We've been getting by here in the meantime. Anyway, just be a little bit more convenient if they can look up and see it too. Okay. Okay, good. So you guys that are online, I don't see you come up with any questions for me. Is it because you haven't tried the exam yet? I think that's it. You people are afraid to try the exam. You know, you have to do it anyway. You might as well dive in. You have to do it anyway, right? So let me while we're talking about this, let me open up. Let me just get something to write on here. Okay, so what else are you likely to come across on this test? Okay. Okay, so let's talk about what we covered this semester that's likely to wind up on this test. Well, first thing that we covered, which I tried to emphasize how important it was. I know that it doesn't seem important and it seems trite and trivial, is data types. Because as we go on in the semester, understanding what the type of data is going to determine how you work with the data, work with the statistical analysis, what type of analysis that you choose, how you analyze the data, how you handle the data, and so on and so forth. So you're definitely going to get questions that ask you about data types. Okay, and I'll give you some examples. You know, I don't remember what the examples are, but I mean, it could be even things like, it's just right now, heads or tails. What kind of variable is that? Coin flip. That's a categorical variable, right? I don't think I'd ask you if it's binomial or not, because that gets into those other problems, but that's a categorical variable. How about other kinds of categorical variables like hair color, right? Well, they can have more than just two values. They can have, you know, brunette, blonde, redhead, so on and so forth. How about so the categorical variables? But I mean, other things, anything that's a name is a categorical variable. Country, a borough, the 5 boroughs in New York City, right? Categorical variable. Zip codes are categorical variables. Why do I say that? They look like numbers. Yeah, they are numbers, but they represent an area. In other words, instead of saying Bensonhurst, you might say 112. I'm going to take a while. 11223. I'm going to take a wild guess, right? Long Island City, 11301. I'm guessing, right? So they're not really numbers. You can't add them together. If you want to combine 2 zip codes, you can't just add the 2 zip code numbers. They're names. They look like numbers, but they're names. That's a nominal variable. There are also other kinds of nominal variables that have, besides being a name, they have a sense of order, natural sense of order. So for instance, when you buy eggs, you buy, I don't even know what the normal, nobody buys normal size eggs, I guess, right? Because it's always large, jumbo, extra jumbo, whatever. And you never see just an egg, right? It's always got something after it, right? So what do those represent? Well, they're names. They name the type of egg, but they also imply that the next one is larger than the other one and larger than the other one. Are they precise? Well, you know, I think they are within a certain range, but we don't know what that is, right? The USDA probably knows what that is. All we know is that jumbo is bigger than extra large is bigger than large, and so on and so forth, right? So we see that as an order. It may not be the same between each. In other words, the difference between large and extra large might be different than the difference between large and jumbo, right? But we don't know that. All we know is they have an order. How do you feel today? Good, better, best, right? So I mean, that's a nominal variable, and we know best is better than good, is better than poor, and so on and so forth. So they're nominal also, except they're a special form of nominal that we call ordinal. They have order. They're really nominal variables, but they have order, right? So you might have an example of that. And then finally, there's the big category of variables that we use very often, which is numerical variables, right? And that's anything that's on the number scale, blood pressure, height, weight, so on and so forth, where the units are defined. Difference between 10 pounds and 20 pounds is the same as the difference between 20 and 30 pounds, and so on. So that's a scale, right? Scalar variable. Could be a logarithmic scale, could be a lot of things, but it's on a scale that's definable. So we might occasionally also run into a numerical variable that by its nature is a count or an integer. Number of siblings, for instance, 3 siblings or something like that. Number of cups of coffee you drank today. Number of people living in your household for the census, for instance, right? It's not going to be 9.5 people. It's going to be, they're going to count each person, right? So that is a numerical variable, but it's a special type called the discrete numerical variable. And usually, if it's something that you would define as something you would count, like, you know, you would fit your finger, just put your finger on it and count it, that's probably what you would define as a discrete numerical variable, right? So I think if you can kind of hang on to that, you'd be in pretty good shape. So beyond numerical variable, what else did we talk about? We talked about histograms, box plots, histograms, and so on and so forth. So it would not be surprising if you got an example of a box plot. right? So here, this might be a box plot, like so, right? And here's the scale over here, and this is 100, and this is 20 down here, and this is 40, and this is 60, and there's a bar going right across the middle here, a thick bar going across the middle here. Okay, so what do we know about that? We know that this represents the highest value in your sample. This represents the lowest value in your sample. The bar in the middle represents the middle value, the median, right? The median is also called the 50th percentile. 50% of the people are above that, 50% of the people are below that. 50th percentile, right? So this other box that's that's in here, the lower edge of that box represents the 25th percentile, and the higher end represents the 75th percentile. Okay, what is that called? That's called the interquartile range, IQR, or interquartile range. The middle two quartiles, right? Middle two 25%. So 50% of the people in this sample or population are between 40 and 60, right? What if we got a little dot down here, a little star or a little dot down here or something like that? What does that represent? That represents a value that's so far from the other values that you might look at it as possibly being not representative of this population. In other words, those are what we might call outliers. Now, who decides what an outlier is? When you do a box plot in SPSS, SPSS uses a rule inside of SPSS to determine what a outlier is. And I believe it's something like 1.5 times. If it's more than 1.5 times the distance from the 50th percentile to the 75th percentile, or the other way around, it's 1.5 times that, then I think it defines it as an outlier. Can you change that? Yeah, you go into SPSS, change the settings, and tell it, I don't want you to use that. I want you to use twice. I want a wider range. I don't want to eliminate what values I don't think are okay. But really, when you start to look at that and you see that, it's really an indication to you that you need to check that data and see if it's improperly entered, if it's not representative, to decide whether you want to include it in your statistical calculations or not, whether you can justify dropping it, and so on. Okay, so what else might we wind up with graphically? Well, histograms, right? You might wind up with a box plot, a bar plot, for instance, for, let's say, right-handedness, right, where this represents left-handers and this represents right-handers. You can see that there's more right-handers than there are left-handers, and the height represents the frequency or a number of people in your sample or in the population that represent left-handers or right-handers. Well, we can go further and get a numerical variable, and we can break that numerical variable up into categories, up into ranges. So for instance, each one of these bars represents the frequency in a population or in a sample where we count people that are within a certain range. So for instance, if this is height, this first bar might be 55 to 60 inches. 55 to 60 inches. Next one might be 60 to 65 inches, 65 to 70 inches, 70 inches to 75 inches, and so on and so forth. And you'll notice that unlike the bar plot for the categorical variable, handedness, these are all connected. And they're connected because the minute you go past 69.999 inches, you flop into the next category. It's continuous. And you can define, you can get SPSS to produce one of these. SPSS will look at the data, make up its own mind on what to use as the ranges. Is that like carved into stone? You know, like the 10 Commandments, you know, Moses came down with the 10 Commandments? No, you can actually adjust that. Tell SPSS, you don't want 7 bars, you want 14 bars. So it'll make the bars narrower, or maybe you don't want them as narrow. So you can adjust that if you want. Okay, but what does this tell you? This gives you a general idea of the distribution of the values. Now, even if you're just looking at it, we took this even further and we looked at it in terms of a normal distribution. And you remember we looked at the empirical rule and we looked at the the z-table and so on and so forth. So we looked at that and we used this to figure out probabilities of sampling people in a population. So that worked out pretty well for us. But even if it's just a histogram, you can still look at it certain ways. So for instance, what percentage of the people are less than 65 inches tall? Well, let's see. If I count up all the heights of these, each one of these represents a certain number of people in a population or sample. If I count up all the heights of these, this might represent 100 people, right? So if there are 20 people here and 10 people here and 5 people here, that represents 35 people that are less than 60 inches tall, right? So 35 people less than 60 inches tall out of 100 is 35% of the population is under that height. And you can figure out what percentage is between this height and this height. You can figure that out of 100. Then we could also look at this in terms of conditional probability. So for instance, given that you are shorter than 60 inches, what's the probability that you're also shorter than 50 inches? Well, less than 60 inches, only 35 people are less than 60 inches, and there's only 5 people that are less than 55 inches. So the probability, given that you're in this group of 35, is 5 out of 35, or whatever 1/7 is, right? Whatever that turns out to be, maybe 0.16 something, whatever it turns out to be, right? So that's a conditional probability. And conditional probability starts to come up as something else as we moved on. Next thing we examined was this idea of diagnostic tests. And one of the reasons we did that because we had a good example of the application of conditional probability. Okay, so in a diagnostic test, right? When we look at a diagnostic test and the results of a diagnostic test, right? You're usually testing people to see if they have a disease or condition. Okay, so if you have 1,000 people, right? And the columns represent people who have the disease or people who don't have the disease. And the rows represent people who test positive and people who don't test positive. Okay, so if we have 1,000 people, if the prevalence of disease in this population is 10%, I would expect out of 1,000 people, 100 of them have the disease, right? This whole vertical column would add up to 100 because out of 1,000, not so many people have the disease, and 900 would not have the disease. So now let's say you test those 100 people. And it turns out that when you test those 100 people that have the disease, 90 of them test positive and 10 of them test negative. First of all, what do we call that 90 that test positive and have the disease? Everybody remember? True positives, right? Okay. And what about the 10 people that have the disease but test negative? What do we call them? Are they positive or negative? The test. They're negative, right? Is it correctly negative or incorrectly negative? It's incorrectly negative. They tested negative, but they have the disease. So it's a negative test, but it's wrong. It's a wrong negative test. So it's a false negative, right? Okay, what about people that test negative that don't have the disease? That's a true negative. And people who test positive that don't have disease that test positive, that's a false positive, right? So in this case, let's say that out of 900 people, 90 of them test positive and 810 of them test negative. So all the people in the top row are people who tested positive. 90 plus 90 is 180. And all the people in the bottom row tested negative. 10 and 810, that's 890 negative tests. I blew it here somewhere, didn't I? What happened here? 90, 900, 810, 900, 90 and 10, 90 and 90 is 180. 10 is, excuse me, this is 810, 820. Excuse me, 820. Right? That adds up to 1,000 now. Okay, so how many people tested positive? Right? Well, we got 90 people that tested positive that had the disease. Good. But we got 90 people who don't have the disease that tested positive. So 180 people tested positive. Wow, 180 people. How many of them actually had the disease that tested positive? Only 90. So 90 out of 180 people that tested positive actually have the disease, right? That's called, and that's equal to 0.5, 50%. That's called a positive predictive value. In other words, if you took this test, you and 180 people that took this test and came out positive, there'll only be a 50% chance that you actually had the disease. Make sense? Right? So that's the positive predictive value. That is a conditional probability, right? Why is it a conditional probability? So that's the probability that you have the disease, right? And I'm going to use that pipe command, that pipeline, that line, given that you tested positive. Okay, that's a conditional probability. That's what this is equal to, right? So we can also look up the negative predictive value, the probability you don't have the disease, given that you've tested negative, right? What's that going to be? That's going to be how many people tested negative? 820. How many people tested negative that have the disease? That don't have disease is 810 out of 820. 810 people tested negative, don't have the disease out of a total of 820 that tested negative. So that's going to be that negative predictive value is going to be, I don't know, 98%, let's say. I'd make that number up, but you guys can figure that out if you divide it in. Okay, so that's our negative predictive value. Okay. So there's some, you can go online and you can, I think I even put some links on Blackboard to places where you can put the numbers in and figure this out for yourself. You know, you can have it do the calculations for you. So negative and positive predictive, so that we learned about that. Next, we moved on. Oh, by the way, there was one other thing, the Venn diagrams. Remember those things, those nasty things? Okay. Let me talk about them briefly. Okay, let me clear out all this junk. Okay, let's take a look at our Venn diagrams. Okay, so let's take a look. Let's say we have two groups, Group A and Group B. Group A and Group B. Okay, so I'm going to tell you that A is a probability that you are left-handed. And how'd that work out? He's getting there?
But I got it.
Okay, good.
Thank you for everything.
No problem. I didn't do anything. You did all the work. You did all the heavy lifting. Probably, yes?
Will you be like over the week or anything, like if they have questions,
Post-
email?
Post to the discussion. Usually I'm okay with emails and stuff like that. You got to put the class number in the, if it's a personal thing, email it to me. If you're really shy or you're embarrassed, you can email it to me. But I would prefer you go to the discussions forums. And on the discussions forum, there's one thread for questions on homeworks and another thread of questions on the exam. And the reason why I'm doing that is because if I give you some advice on the exam, I want the other students to be able to see it also, right? Because otherwise, well, I don't hesitate to talk. So it's like, I'll spill the beans. I'll give away the ranch, and then like it'll, if you ask me a question. So it's better if everybody sees my answer. Not only that, but a lot of them, when they take the exam, they're going to have the same question that you have most likely. Okay,
That's
so
basically what
you can
you're
always
doing
email
now,
me,
right?
just put your PH750 and stuff. But I prefer if it involves the exam or something like that to put your question there.
And you're just taking exam questions right now, review questions?
Yeah. Matter of fact, I was encouraging it, but nobody's asking me anything.
Are you recording?
Yes, I'm recording. Okay,
So they're gonna have
good. Yes.
all my nervous.
Okay, yep.
Here.
Okay, so yeah, I'm just, right now, since nobody's asking me a specific question, I'm just kind of doing a general review of things that you're responsible for in the test, that you can expect to see on the test. Okay? All right, good. Let me get back to this. No problem. Okay, so probability of A represents the population that is left-handed, and B represents people that have, what can I come up with? Let's see, that have, I'm drawing a blank now. Left-handed and are rich. How about that? Okay, both left-handed and rich, right? Okay, so if I want to describe only the people that are left-handed, I would just say that I'm concerned about A. That would represent everybody that's in group A, including this part that overlaps with group B, right? What about the people that are rich? People that are rich are just B, right? Okay, what about the people who are either left-handed or rich? That would be union. A, union B represents everybody that's either left-handed or rich, right? So that would represent everybody here. Everybody on this side is left-handed. Everybody here is rich. Everybody in the middle here is both rich and left-handed, right? So that would be A union B. Well, what about the probability that you're both left-handed and rich? Well, left-handed and rich would be intersection A intersection B. That means that you have to have both properties, A and B at the same time. So the only people that would apply to are the people in this area here that are both rich and left-handed. Okay, well, what about that? That seems like everything we could possibly ever want to know about this, we have now. Well, how about a situation where we ask, what about the people that are not rich? We could indicate that as B prime. So what area would B prime, not rich, represent? Well, it would represent all of this area. I'm going to draw this in now so you can see it. All of this area. Why am I not including this area? Because they are rich, right? Even though they're left-handed, they're rich, right? So that doesn't include them. What about not A, right? Not A would be the same thing except just the B's, not the part that overlaps with the A's. Okay, and what about if I wanted to describe this? Another way I might describe this is A, let's see, A union, A intersection, not B. What would A intersection not B mean? That means it has to satisfy both of those conditions. It has to be A, but not include B, right? So that's the same area I just drew. It's another way of describing the same area I just drew here. Okay, so I don't want to get into too much of this. I'm not even sure. I think there are some examples there, but you want to know something, dirty little secret. I think if you go back to the PowerPoints, I think we'd go through almost every possibility in either my PowerPoint or Levi's PowerPoint. Right, so if you look at them, look at the PowerPoint, you'll see we went through a number of examples there that probably would help you out. Right, but that's a possibility you might see this on the exam. Okay, so next. So now I got to clear this. Erase all drawings. Good. And now finally, I'm not sure, but I think finally. The other thing we covered recently this semester is this idea of normal distribution. We introduced the normal distribution. Okay, and in the normal distribution, we expect to see a distribution which is basically kind of like our histogram, except it represents a smooth curve, very large population, for instance, a smooth curve, where the mean is in the center. Okay, and it's in the normal distribution, the mean would be in the center, the mean and the median would be the same value. And this would be bell-shaped, and it would be symmetrical around the mean. This side would be the same shape as the other. You could flip them over, you could fold them over, and they would match identically. And we could describe these as being based on being population with mu and sigma, the standard deviation. We can describe the shape and the distribution of this population with just the mean and the standard deviation. So let's say I said that the mean was equal to 100 and the standard deviation is equal to 10. Okay, so the empirical rule, right, just an overall assessment. I won't try to write this out too much because I'm using my trackpad. The empirical rule tells us some basic facts about this normal distribution. These are estimates, they're not perfect, they're estimates. It tells us that the distribution is such that if you go for any normal distribution, if you go one standard deviation below the mean and one standard deviation above the mean, I'll just put this as down as -1 standard deviation. I'll put this down as +1 standard deviation. If you go that far away from the mean on the left and the right, that in between here is approximately 68% of the population. Right? I could look at it that way. I could look at it another way, and that is that since the population is distributed this way, I could say if I took one random individual from this population, selected one random individual, the probability he would be between one standard deviation below and one standard deviation above is 68%. Right? And if I went out further, 2 standard deviations below, 2 standard deviations above, you guys know what that is, right? Remember? Right? That would represent 95% of the population. Right? That's 2 minus 2 standard deviations and plus 2 standard deviations. So in the case of this distribution, standard deviation, the mean is equal to 100, standard deviation is equal to 10. What would these numbers be? This would be 100. 1 standard deviation above would be 110. 2 standard deviations would be 120. Below would be 90. And 80, right? Pretty convenient to know this kind of stuff. So now I could ask you, well, what's the probability that that if I randomly selected one person from this population that let's say it's blood pressure, their blood pressure would be below 80. What's the probability that they would be below 80? Well, where is below 80? Below 80 is just this little area down here, right? And below 80 is going to be the same area as above 120. Why is that? It's because it's symmetrical, right? So how much have we accounted for here? We've accounted for 95% of the population. What's missing? 5% is missing, right? So it's got to be in those 2 tails of this distribution. Since it's symmetrical, that 5% is divided exactly equally between the top and the bottom. So there's a 2.5% chance that you have a blood pressure in this population below 80, or for that matter, above 120. So now you could just look at this and say to yourself, well, 68%, since it's symmetrical, this is 34%, and this is 34%, right? And gee, if this is 68, this is 34%, that means from here down, including that 2.5%, is about 16%. And from here up, is about 16%. So now you can use this to help you answer all sorts of questions about what's the probability of being between 90 and 120. That's this area in air, right? You could figure that out by adding and subtracting these various areas. Okay, so I won't go into too much of that. So now what about if we need to know this more exactly, or if our number of standard deviations that we're interested in is not an exact number, okay? It's not a nice even number, right? Let's take a look at this. Oh, and by the way, this is true whether it's a nice big distribution like this. I can't undo. Okay, let me clear this. Or it doesn't matter if this looks like this, or if it looks like this. Okay, these two have the same mean, right? 100. The standard deviation of this top one might be 5, and the standard deviation of this bottom one might be 20, right? Okay, but the empirical rule still says the same. In other words, 68% of the population here on this top one is between 5 below and 5 above, or between 95 and 105. For this bottom one, it's between 80 and 120, because it's always going to be, 68% is always going to be one standard deviation above the one standard, no matter what the standard deviation is. So that's how you can describe all normal distributions using these formulas. So now let's take a look at a situation where we got to go a little further than that. Clear this out. Okay, let's see what we're going to do here now. Let's say we have a normal distribution, and I'll go with something easy again. Okay, mu. I'll call mu is 100. And standard deviation is equal to 10. Okay, so what if I asked you, what's the probability that X, the value we're interested in, let's say this is blood pressure, that X, or BP, if I put that in there, right, is less than, let's say less than 87. Wow, okay, how many standard deviations below the mean is 87? Gee, let's see. One standard deviation below is going to be about 90. 2 standard deviations below is going to be 80. So 87 is somewhere in here, right? Somewhere around there, right? So what I'm interested in, the area below this, probability of being less than 87. Well, I can't use the empirical formula, right? Because it doesn't come up in even number standard deviations, a integer number standard deviations. So how many standard deviations is this? Well, an easy way to, I can see it's 13 below the mean, and the standard deviation is 10. So you can see intuitively it's 1.3 standard deviation below the mean. But we can apply a formula here. We can say that Z, and from now on, when I use Z, it's going to be the number of standard deviations is equal to the number we're interested in minus mu, the mean, over the standard deviation. You'll see this will work just as well, right? 87 minus 100 over 10, which is the standard deviation. Now, minus 100, this is going to be a minus 1.3. Notice using the formula helps me keep the sign straight. Well, what does that mean? That means that the area we're interested in is to the left of the mean, right? Negative 1.3. So I have to look it up again. Agresti table. Oops. Why is it doing that? Okay. Not cooperating. All right. Tell you what. Why is it doing that to me? Maybe because I have the, oh, you know what it is? I think I have the pen. I have the pointer turned on. Okay, I think I can do this now. Yep, that was a problem. Okay, I'm gonna have to look through this because I don't want that to go away yet. Okay, so I'm gonna use this first table because the first table represents areas below the mean. Second table represents areas above the mean. Right, so the area below the mean. Okay, so it's going to be 1.3, 1.3, and we know these vertical columns represent the third digit. 1.3 is 0 is implied. So it's 1.30, which is 0.0968. I'm going to call it 0.097 for our purposes right now, 0.097. So this area, is equal to 0.097. Probability of me picking person from this population has a blood pressure below 87 is 9.7%, or probability is 0.097. Okay, or you could also say the percentage of the population that has a blood pressure below 87 is 9.7%. I could have asked you, what's the probability of someone in this population having a blood pressure greater than 87? What would that be? That would be the same thing. 87, I'd get this area is 9.7, but I'm interested in what's above that. So it would be 100% minus that, right? Or in other words, this would be 90.3%. Or as a probability, 0.903. Make sense? Okay, so what else might I ask you about? I might ask you, for instance, what's the probability of somebody being between probability of someone's blood pressure, their blood pressure being between 87 and 96, right? What's the probability of being between those two things? Well, that would be the probability of being between 87 and say 96 would be about here. Both of them are to the left of the mean as it happens, but that's okay, right? We want that area right in there. How would we figure out what that is? We would take this area first, the area below 96, we would calculate the z-score for that. Look up on the z-table the area that represents, calculate that area. Then we would take the area for 87, which you already know is 0.097, right? And let's say for argument's sake that this area was 40%, 0.400. Okay, I would then subtract our 9.7% from our 40. It would leave the area between the two of those, or 30.3%. Okay, I'm making those numbers up. You would actually look them up on the z-table. So you can use that z-table that way. I want to show you one more thing about the z-table. Okay, let me just erase this. Oops, that's not what I want. Right there. And result drawings. Okay, good. The one more thing I want to show you about z-table. Okay, so here's our distribution again. Same distribution. What the hell? 100, standard deviation 10. Okay, so what if I asked you, what is the blood pressure of the lowest 10% of this population? Where is the lowest 10% of this population? The lowest 10% is the people who occupy this area of the distribution, where this area is equal to 10%. I'm going to say 15%. What's the lowest 15% of the population? Okay, so if I ask you, what blood pressure below which you have 15% of the population, how would you figure that out? Well, you know the mean and the standard deviation, and you have your z-table. The z-table, whoops, I got to turn off this. I got to use my pointer. The z-table represents the areas. The numbers in the middle represent the areas of the curve, normal distribution. The numbers at the edge represent the z-score. So I can use it in reverse. If I want to know what's the z-score of the value that has the lowest 15% in this population, okay, I would look up the area that represents this shaded area represents 15% of the area of the distribution. So I'm going to go down here, I'm going to look for the closest thing to 15%. 0.15, 0.1492, same year. Well, Columbus Day, 1492. There you go. Right. It's not Columbus Day anymore, right? It's, what is it? It's Indigenous Peoples Day. Right. Okay. And you're hearing that from an Italian. Okay. So 1492. I didn't do that on purpose, by the way. By the way, we have no class on Monday, Columbus Day. You guys know that, right? School's closed. Okay, so 0.149, I'm going to call that 15%, right? I'm going to say that that's our 15% right there. What is the z-score that represents that area? It's negative 1.04. Negative 1 the z-score there is negative 1.04. I got that right, didn't I? You'd tell me if I got it wrong, wouldn't you? Right? Am I right? Let me go back here. Negative 1.004. Yeah. Yeah. Okay. Negative 1.04. The z-score is negative 1.04. Okay. So remember that formula I showed you before? Z is equal to X, the value we're interested in, minus the blood pressure, in other words, minus mu over sigma. What do we know about this point over here? We know Z, we know the mean, we know sigma. There's only one thing in this formula we don't know, and that's X, that's the blood pressure. So negative 1.04 is equal to X minus mu, which is X, we don't know what that is, minus 100, which is mu, over the standard deviation, which is 10, right? So now I can cross multiply here, just to get all this worked out here. So negative 1.04 times 10 is equal to X minus 100. Whoops. Okay, so 1.0 times 10. So negative 1.04 times 10 is negative 10.4 is equal to X minus 100. So there's an equal sign there. So if I bring this 100 over to the other side, it becomes 100 plus 100 minus 10.4 is equal to X. Okay, and if I subtract, it's going to be equal to 89.6. 89.6 is equal to X. So in other words, the blood pressure that represents the point at which, below which 15% of the population has that blood pressure that or lower is 89.6. Anybody has blood pressure above 89.6 is in the top 85% of the population. Okay, so if you can do that, you should be if you can do what I just did here, you should be able to get through this test without too much of a problem.